Greetings to all. We are Team 15. Today we are going to present our 5th SEM OS Lab project. We have made a simple desktop based GUI application which simulates CPU scheduling algorithms. Now let's make you familiar with all the controls. Here we have implemented total 8 algorithms with priority and preemptive priority. And as you can see, all of these algorithms also work with IO burst time. On clicking this IO button, we can see here an IO key is also added for animation. Here the number of processes are to be added so that table forms and we can enter details in that. This is time quantum when we have to add preemptive processes. Here our whole animation is clock synchronized, so here the clock timings will be shown. There are 3 buttons to start this animation, to reset the animation, and this is random. The function of random is to fill the random data if someone have to visualize the animation and not to fill the data. So let's quickly start all these algorithms. First of all comes FCFS. Let's put number of processes as 3. We will keep it short, and randomly any data we select, we have to select some small time. So let's start. You can see here basically at each second what is happening to each process can be easily visualized in this animation. Whole thing is clock synchronized. Now after the completion of this process, when you go further down, you will see the whole detail. You will see average TAT of each process. You will see average TAT and TAT of each process. Here you can see the total context which is taken, the total stall pulse, and the efficiency of the algorithm for the following details. And further down you can see a Gantt chart. Now here you can easily visualize what happened to which process at which time. So let's quickly complete all our other algorithms. Moving towards SJF, we select 3 process, again random data. Oh, we haven't reset it, so let's again reset and start. So you can see after process 2 it will take process 0, it will take process 2 because it's SJF, and after that finally process 1. And again if you go down, you can see efficiency of SJF, and you can see the Gantt chart. Now let's select some other process. Let's say we want LJF and we want this same data. Now you can see that SJF performs with 75% efficiency. Let's see how LJF will perform. We would just reset the animation and we would click start. On the same data, you can see after P0 now P1 comes and not P2. After all this, if we go down, yes, probably the efficiency won't change because the data was too small and the completion time was exactly the same, so we hadn't noticed any change in efficiency, but you can easily see the change in wait time and all. Now trying another algorithm, let's see RR. Now here we will select 4 number of process. TQ would be, let's say, 2 time quantum, random data, and start. We again forget to reset. Let's start. Now you can see after 2 time quantum again process P0 again comes in CPU. All these processes are in CPU for 2 time quantum only, and you can see the whole thing is completed. Similarly, going down, you will see the efficiency. RR performs very poorly because context switches are lot here, as we know. And here you can see the Gantt chart easily, which process came how many time and all. Let's move towards SRTF. And let's say we want this same data, we would reset the animation and we would start. Let's see if there's any difference in efficiency from RR. Yes, so we can see that shortest burst time also performs same on the similar type of data. Here you can see the Gantt chart. Because the completion time and context switches are same, they will definitely perform same. Let's see LRTF on the same data. Let's reset and let's start. You would notice the change in completion time and TAT here. You see, again going down, you can see the change in waiting time, you can see the change in TAT, but efficiency won't change because number of context switches which took are same, and that they are dependent solely on your time quantum. Because the data was same, completion time was same, and you can see the Gantt chart for LRTF also. Going further ahead, let's see what's we get in priority. But here we have to select the number of process again so that this table will change and we can get the column of priority. Now you can set here the priority. Again we would choose random data, and here is the data, and 8 priority is lower than 1. Let's reset the animation and let's start. So as you can see, because arrival time was 0, it was first, and animation is over, and here there's no waiting, so no graph is created. You can see the Gantt chart. Let's change our algorithm to finally preemptive priority. Let's have 3 preemptive priority with TQ of 2. Let's put random data in there. Let's see if I want this data. We can also change manually. If I don't want arrival time to be 1, we can change it to 3. And here I don't want, you can put it 2, but conventionally if we go, we can put here 4, like in a ascending order. So let's reset the animation and start it. Here P0 comes because its priority is higher. And P1's priority is lowest. So after that, you can see here the charts. P0 has no waiting time, and the Gantt chart. Finally, all our algorithm without IO are over. So let's start FCFS now. This time it is with IO. So you can see IO queue is added here. Let's have number of processes as 3. This time let's have number of processes as 5. And this time I would like to add data manually. So let's say if this is the data, here you can see 2 processes have same arrival time, but yes, our algorithms deals with it also. So if we have this kind of data, and we will keep it same for all other algorithms which includes IO. We have reset the animation. Now let's start. So you can see that P0 now goes to IO, P1 goes to IO, because in IO there is no compulsion that at a time only one process can run IO. So every process runs IO simultaneously, and this gives a better performance. Here you can see everything: efficiency, context switches, and for 5 processes you can see TAT for each process and an average TAT. You can see waiting time for each process and average waiting time. Now after that you can see Gantt chart. You see every process has comes 2 times in CPU, and that's why there are 2 bars for every process, because once it comes in CPU then it goes for IO and then again it comes in CPU. Let's see another algorithm in IO. For the same data we would reset the animation, and I guess efficiency was 60. Let's see here, start the animation. You can see here what's happening to each process at each clock pulse. It's fully time synchronized. So you can see here the efficiency has taken is a bit low. In FCFS the efficiency was 60%. Here is it's showing 57%. You can see the Gantt chart and all. Let's see another algorithm. Let's say we want LJF. For the same data we would start the animation. You can see P1 is now in IO, P2 is also in IO, P0 comes in IO, P3 comes in IO. All this data is changing here constantly, and I guess P1 comes again, P0. Every process comes in CPU twice, and I guess it's over. So again here the efficiency is 60, so it's better than last time. You can see the waiting time. P0 takes the most waiting time because it comes here and it gets chance again here. You can see in the CPU. Same you can find in Gantt chart also, that it comes for the first time here at 6 units of time, and then again it comes at 24 unit of time, and for what, for only 1 BT. So yes, P0 suffers more waiting time. Let's see round robin scheduling for the same data, and here also let's say the time quantum is only 2. Let's reset this animation and start. P4 has only one IO, so that completed very fast. And again for 2TQ, it gets completed at the same time. Let's see, efficiency is 40. You can see the efficiency is too low than standard algorithms. Why? Because context switches are more in round robin, as you know. and you can see the Gantt chart easily. Now let's try SRTF, but this time I would keep the time quantum at 1. Let's see what happens to our efficiency. We would reset this animation and we would start. You can see a process is coming very much. You can expect very low efficiency because context switch would be obviously very high. Here to increase efficiency, we can manually attach some mechanism, some hardware mechanism, so that context switch doesn't, you can see, or almost it shows zero efficiency because efficiency is too low. Context switches are too high. There are 25 context switches and total completion time is 25 because we haven't add this time of context switches. If we consider time of context switches as 1, then total completion time would be 50, and time of context switches is from that is 25. So efficiency is too low. We can see the Gantt chart here. As I said that in real time, if we want to implement SRTF, then we have to have uh, some mechanical things that would manually decrease the context switching. Let's have LRTF. This would have more context switching. Let's see if we have TQ3, then what result we get. Let's start this animation. You can see here it goes into IO. And all IO is completed. And let's see the data. Efficiency is nice because TQ was a time quantum we selected was 3. And like this, you can also visualize that which time quantum is best for which algorithm on what type of data. So you can get a wholesome idea. Now let's select last two algorithms. For the same data, I would reset the animation. I would select number of processes again because this is priority, and as I said, for priority column to appear in this table, we have to again select number of processes. Let's fill random data in it. IO is too high, I know, but yes, it could work. Let's start. Here you see P0 process because it was first arriving. Now P1 because it has higher priority, and you see the for random these two priorities are same. So what happens? Let's see. You can visualize that P3 is in IOQ still, and now P2 comes in IOQ after completing its time. So now as you can see, the process is finally completed at 35 units of time, and you can see the efficiency is high, and there is also one stall pulse. At 1 unit of time the CPU was just idle. You can see the average time for priority, and here's the Gantt chart. So let's see the preemptive priority. In this case we would uh, take time quantum as 2 units. The same data, I would just reset the animation and start the animation again. Now you can see this processes would come again and again. It would switch and come again. just like round robin but with priority. Here the P3 is in IOQ. So at time quantum 39, I guess it completes. And here the efficiency is low compared to priority, which is very obvious because context switches are more. There are 20 context switches, and you see 5 stall pulses are also there. For 5 units of time, CPU was just idle. So all this uh, combines, and you see all this will decrease your efficiency. And here's the Gantt chart. So here we are completed all our processes, and we hope that this animation would contribute towards better learning of and better understanding of scheduling algorithms in operating system. So I am very thankful to my team consisting Shrishti Darbar, Vaidehi Shah and Sameep Sharma. With all of our collective efforts, we successfully carried out this project, and we will be uploading this project on GitHub, and all our viewers are invited for further contributions. Thank you.